Have you ever stared up at the night sky and noticed how certain areas seem almost empty, like blank spots on a map of the cosmos? Those aren't just gaps in our vision. They're cosmic blind spots, places where the universe itself seems to hide its secrets. And there's one region lurking behind the thick curtain of our own Milky Way that has puzzled scientists for over a century. It's called the Zone of Avoidance, and it's one of the most mysterious frontiers in all of astronomy. Imagine trying to study a distant city, but there's a towering, fog-covered mountain right in front of you. No matter how hard you squint, the details are lost in the haze. That's exactly what astronomers face when they look toward the Zone of Avoidance. Our galaxy's swirling arms, packed with stars, gas, and dust, block our view of whatever lies beyond. For generations, this region was dismissed as an impenetrable void, a place where telescopes simply couldn't see. But what if I told you that behind that cosmic veil, there could be entire galaxies, superclusters, even anomalies that challenge everything we know about the universe? This isn't just a story about what we can't see. It's about the relentless curiosity that drives us to uncover the hidden. Scientists have spent decades developing ingenious ways to peer through the Milky Way's glare, using infrared telescopes, radio waves, and even gravitational clues to map the unseen. And what they've found is astonishing. Galaxies where there shouldn't be any, strange structures defying explanation, and hints of cosmic forces we're only beginning to understand. The Zone of Avoidance isn't just an empty space, it's a puzzle waiting to be solved, a frontier teeming with discoveries that could rewrite our understanding of the cosmos. So let's embark on this journey together, beyond the limits of our sight, into the shadows where the universe keeps its deepest secrets. The Zone of Avoidance isn't an actual place, it's more like a cosmic blind spot. A vast swath of sky where our view of the distant universe gets swallowed by the Milky Way's thick band of stars, gas, and dust. Picture standing in a crowded room, trying to see someone on the other side, but everyone in between is holding up giant, glowing posters. That's what astronomers deal with when they point their telescopes toward this region. The light from billions of stars in our own galaxy drowns out the faint whispers of galaxies lurking behind it, creating what looks like an empty void. But here's the twist, it's not empty at all. The name Zone of Avoidance comes from an era when scientists literally avoided studying it because it seemed like a dead end. Early telescopes couldn't penetrate the Milky Way's glare, so astronomers focused on clearer patches of sky instead. It was like ignoring a locked door because no one had the right key. Over time, though, that attitude shifted from avoidance to obsession. Why? Because every time we've pushed past a cosmic blind spot in history, we've stumbled onto something revolutionary: black holes, dark matter, entire galaxies hiding in plain sight. What makes this zone so stubbornly difficult to study isn't just the sheer density of material blocking our view. It's the way our galaxy's dust scatters and absorbs visible light like fog bending a flashlight beam. Traditional optical telescopes hit a wall, but modern astronomy doesn't give up that easily. By switching to wavelengths like infrared and radio, which can slip through the dust like ghost signals, we've started peeling back the curtain. And what's behind it? Not just a few stray galaxies, but entire clusters, structures so massive they shouldn't exist on the edge of our cosmic maps. The Zone of Avoidance isn't a blank space. It's a mirror held up to our own limitations, challenging us to look harder, dig deeper, and question what else might be hiding just out of sight. The story of the Zone of Avoidance begins not with high-tech telescopes or cutting-edge algorithms, but with simple observation, human eyes squinting at photographic plates in the early 1900s, puzzling over strange gaps in the cosmic tapestry. At the time, astronomers like Edwin Hubble were just beginning to grasp that the universe extended far beyond our Milky Way. As they mapped distant galaxies, they noticed something odd. While the night sky was sprinkled with these island universes, there was a glaring absence along the plane of our own galaxy. It wasn't that galaxies stopped existing in that direction. It was as if something was obscuring them. Hubble himself referred to it as a zone of few nebulae, a cautious description that hinted at mystery rather than emptiness. Those early photographic surveys revealed a jagged band across the sky where extragalactic light seemed to vanish, like a river of darkness cutting through the universe. At first, some astronomers wondered if this was evidence of a literal void, a place where galaxies simply didn't form. But Hubble and others soon realized the truth. The Milky Way's dense disk was acting like a cosmic smokescreen, its interstellar dust and stars absorbing and scattering the light from anything behind it. This revelation sparked a quiet revolution in astronomy. Here was a frontier not defined by distance or technology, but by the limitations of our own vantage point. Early attempts to probe the zone of avoidance were frustrating, like trying to hear a whisper in a thunderstorm. Without the tools to see through the galactic haze, the region became a cartographic curiosity, marked on celestial maps with wary skepticism. But even then, a few bold researchers refused to accept it as a dead end. They theorized that if galaxies existed everywhere else, they must exist there too, hidden behind the Milky Way's brilliance. The real breakthrough came when astronomers stopped relying solely on visible light. Just as a doctor might use an X-ray to see through skin, scientists turned to radio waves and infrared emissions wavelengths that could slip through the dust unimpeded. Slowly, the shadows began to lift. By the mid-20th century, radio telescopes started picking up whispers of hydrogen gas from hidden galaxies, confirming what Hubble had suspected. The zone of avoidance wasn't empty. It was just waiting for us to find the right way to look. Standing in the middle of a dense forest at night, holding a flashlight, you might notice how the trees closest to you glow brightly while anything beyond them disappears into darkness. The Milky Way creates a similar effect on a cosmic scale, except instead of trees, it's an intricate web of billions of stars, vast clouds of gas, and drifting dust grains, all conspiring to blot out the light from galaxies behind them. This interstellar fog isn't just a minor obstruction. It forms a sprawling barrier that covers roughly 1/5 of the entire night sky, stretching like a celestial equator around our vantage point. The Milky Way's disk, where most of its stars and dust reside, is about 100,000 light-years across but only 1,000 light-years thick, a flattened spiral that we're viewing edge-on from within. Imagine looking at a sheet of paper sideways. Its thinness becomes almost invisible, but if you tried to see something through it, the accumulated thickness would obscure everything. Now replace that paper with a colossal swirl of starlight and cosmic debris, and you'll understand why the zone of avoidance exists. The dust particles alone, though microscopic, are incredibly effective at absorbing and scattering visible light. They don't just dim distant galaxies, they erase them entirely from our optical telescope's view, like a cosmic censorship. But the real intrigue lies in the unevenness of this blockage. Some regions of the zone of avoidance are denser than others, creating patches where even infrared or radio waves struggle to penetrate. Near the galactic center, for instance, the Sagittarius constellation hides behind a wall of dust so thick it's like trying to peer through a sandstorm. Yet in other areas, particularly toward the outer edges of the Milky Way's disk, the veil thins just enough to tease astronomers with glimpses of what lies beyond, shadowy hints of galaxy clusters that shouldn't logically be there, given our current maps of the universe. It's not just about what we can't see, but what this obstruction tells us about our own galaxy. The dust isn't static, it's a dynamic, evolving part of the Milky Way's ecosystem, recycled from ancient supernova and stellar winds. By studying how it blocks light, we've learned about its composition: tiny graphite and silicate grains, some coated in ice, all drifting in the interstellar medium. These particles align with the galaxy's magnetic fields, polarizing light in ways that reveal hidden structures. Even the empty parts of the zone of avoidance are teaching us how galaxies distribute their matter, how light travels through cosmic distances, and why some wavelengths punch through while others fade. The challenge isn't just technical, it's philosophical. The Milky Way's obstruction forces us to confront how much of the universe might remain invisible simply because we're stuck in the wrong neighborhood. If we could teleport to another galaxy and look back, our own Milky Way might appear as a blinding streak across the sky, obscuring entirely different realms of the cosmos. It's a humbling reminder that every observation we make is filtered through layers of celestial circumstance, and that the universe's full story might always be just slightly out of view. Breaking through the Milky Way's dense veil required more than just better optics. It demanded a fundamental shift in how we observe the universe. In the 1950s and 60s, astronomers turned to a then revolutionary tool, radio telescopes. Unlike their optical counterparts, these towering dishes could detect faint radio waves emitted by hydrogen gas in distant galaxies, wavelengths unhindered by the Milky Way's dust. It was like swapping out a flashlight for sonar, mapping the cosmos through whispers rather than light. One of the first triumphs of this approach was the discovery of Centaurus A, a peculiar galaxy lurking near the edge of the zone of avoidance. At first glance, optical telescopes saw only a chaotic smear of dark lanes crossing a bright core, a messy blob obscured by our galaxy's dust. But radio waves revealed the truth. Centaurus A was a titanic elliptical galaxy, tearing apart a smaller spiral neighbor in a slow-motion collision. Its radio emissions blazed with the energy of supermassive black holes and jets of plasma stretching millions of light-years into space. Here was proof that the zone of avoidance wasn't just hiding ordinary galaxies, it concealed cosmic monsters. These early radio surveys were painstaking. Researchers spent nights manually tuning receivers, filtering out static from Earth's atmosphere while straining to catch the faint hum of extragalactic hydrogen. Yet with each detection, the zone's reputation as a barren void crumbled further. By the 1970s, radio astronomers had catalogued dozens of hidden galaxies, many with bizarre properties. Some emitted strangely distorted signals, warped by the Milky Way's gravitational pull as their light skirted its edges. Others appeared clustered in ways that defied existing models of galactic distribution, hinting at unseen structures weaving through the cosmic dark. The real surprise came when researchers compared these radio maps with infrared observations, a then nascent technology that could sense the heat from dust-shrouded stars. Where one wavelength suggested emptiness, another revealed bustling galactic neighborhoods. This multi-wavelength approach exposed a critical truth. The zone of avoidance wasn't a single puzzle but layers of them, each requiring a different key to unlock. Centaurus A had been just the beginning. Behind the Milky Way's glare lay not only hidden galaxies but entire new questions about how the universe organizes itself on the grandest scales. The turning point in unraveling the zone of avoidance came not with bigger telescopes, but with entirely new ways of seeing. In the 1980s, a groundbreaking satellite named ERAS, the Infrared Astronomical Satellite, turned its unblinking eye toward the Milky Way's obscured regions. Unlike optical telescopes, which see only the light our eyes perceive, ERAS detected heat. Every object in the universe, from distant galaxies to drifting dust clouds, emits infrared radiation, a warmth invisible to us but unmistakable to specialized sensors. Suddenly, the zone of avoidance wasn't a barrier anymore. It became a treasure map. ERAS revealed thousands of galaxies lurking behind the Milky Way's dust, their starlight absorbed but their heat signatures blazing through like fingerprints on glass. One of the most startling discoveries was the Dwingeloo galaxies, a cluster previously invisible, now unmistakable in infrared. These weren't just dim, distant specks. Some were massive spirals, as large and complex as our own Milky Way, hiding in plain sight. The implications were staggering. If this many galaxies had escaped detection for decades, what else might be concealed? But infrared was only half the story. While eras mapped the heat signatures, radio telescopes like ALMA, the Atacama Large Millimeter Array, tuned into a different cosmic frequency. Nestled high in Chile's deserts, ALMA's 66 dishes acted like a single colossal ear, listening for the faintest whispers of molecular gas and dust. Where infrared saw heat, radio waves traced the building blocks of galaxies themselves. ALMA detected cold hydrogen clouds collapsing into new stars, the faint hum of carbon monoxide in interstellar space, and even the ghostly echoes of galaxies so ancient their visible light had long since faded. Together, these technologies painted a picture the optical sky never could. Take the case of the Vela supercluster. Hidden deep in the zone of avoidance, it wasn't just a few galaxies, it was a sprawling web of hundreds, stretching across hundreds of millions of light years. Before infrared and radio, this structure didn't exist on any map. Now, it's recognized as one of the most massive assemblies of matter in our cosmic neighborhood, tugging on nearby galaxies with its gravity. The real magic lies in how these tools complement each other. Infrared exposes the stars and dust warmed by galactic activity, while radio waves reveal the cold, dark reservoirs fueling future generations of stars. It's like diagnosing a patient with both X-rays and ultrasound. One shows bones, the other soft tissue, but only together do they reveal the full body. Perhaps the most humbling lesson from these breakthroughs is how much we've missed by relying on visible light alone. The zone of avoidance taught astronomers a crucial truth: the universe doesn't broadcast on a single channel. To hear its full story, we have to listen on every wavelength, and even then, there are signals we're only beginning to decode. Among the countless mysteries lurking in the zone of avoidance, none is more baffling than the Great Attractor, a gravitational force so powerful it's pulling entire galaxies, including our own Milky Way, toward it at over 600 kilometers per second. Think of it as a cosmic whirlpool, invisible yet unignorable, its tug felt across hundreds of millions of light years. The strangest part, it lies almost directly behind the densest part of the Milky Way's disk, as if the universe intentionally placed its most enigmatic anomaly in the one spot we can't easily observe. This gravitational puzzle first emerged in the 1970s when astronomers noticed something odd about the motion of nearby galaxies. Instead of drifting apart as the universe expands, they were all streaming toward the same patch of sky, a region near the constellation Centaurus, deep within the zone of avoidance. Calculations suggested an unthinkable concentration of mass, equivalent to tens of thousands of Milky Ways packed into a relatively small volume of space. Yet optical telescopes saw nothing but a starry smear. The Great Attractor wasn't just hiding, it was defying explanation. For decades, the anomaly resisted scrutiny. Early hypotheses ranged from a colossal supercluster of galaxies to something far more exotic: a knot in the fabric of space-time, or even a remnant of a primordial cosmic defect. But without direct observation, theories multiplied while answers remained elusive. The breakthrough came when astronomers realized they didn't need to see the Great Attractor to map its influence. By tracking the motion of galaxies like leaves floating toward a drain, they could triangulate its position and infer its mass. What they found only deepened the mystery. The Great Attractor wasn't alone. Beyond it lay an even larger structure, the Shapley supercluster, a sprawling metropolis of galaxies with gravity potent enough to amplify the attractor's pull. Together, these hidden giants warp the cosmic landscape like invisible mountains, bending the paths of galaxies into a river of motion we call the dark flow. Yet the Great Attractor's most startling revelation might be what it says about our place in the cosmos. For all our maps of the universe, we're still blind to the largest structures shaping our galactic neighborhood. It's a reminder that the cosmos doesn't revolve around us, we're just tiny passengers in a much grander flow, tugged by forces we're only beginning to glimpse. The zone of avoidance isn't merely hiding galaxies, it's concealing the very currents that move them. Modern astronomy has turned the zone of avoidance from a cosmic blind spot into a frontier of discovery, thanks to ingenious techniques that pierce the Milky Way's glare. Among the most powerful are X-ray surveys, which detect high-energy radiation from some of the universe's most violent phenomena. Picture a flashlight beam cutting through fog, except in this case, the flashlight is a torrent of X-rays emitted by superheated gas swirling around black holes or colliding galaxy clusters. Instruments like NASA Chandra X-ray Observatory have scanned the zone, revealing hundreds of previously hidden galactic nuclei and colossal superstructures. One striking example is the Norma cluster, a dense knot of galaxies near the galactic center, bathed in X-rays so intense they betray its presence despite the Milky Way's dust. But X-rays only tell part of the story. Another breakthrough comes from mapping neutral hydrogen, the cold, uncharged gas that fills the space between stars. This gas emits a faint radio signal at a specific wavelength, 21 centimeters. It's a cosmic fingerprint, detectable even through thick dust clouds. Projects like the HIPARC's All-Sky Survey have used radio telescopes to trace hydrogen's distribution, uncovering galaxies the zone had concealed for centuries. The technique is so sensitive it can reveal not just a galaxy's presence but its motion, showing how these hidden systems rotate and interact. Some, like the curiously named Hizoa J083643, drift through the zone with vast reservoirs of hydrogen, suggesting they're pristine relics from the early universe untouched by galactic collisions. The real power emerges when these methods combine. X-rays expose the hottest, most energetic environments, while hydrogen mapping charts the cold, quiet building blocks of future stars. Together, they've exposed the Vela supercluster, a sprawling network of galaxies that rewrote our local cosmic map. Initially dismissed as a minor grouping, deeper observations showed it was a titanic filament stretching across the zone and pulling galaxies into its gravitational web. Without these tools, we'd still be blind to structures shaping our corner of the universe. Yet the most exciting frontier lies in machine learning. Modern algorithms sift through terabytes of multi-wavelength data, spotting patterns human eyes might miss. They've identified ghost galaxies, dim, diffuse systems lurking in the zone's shadows by their subtle gravitational effects on visible neighbors. It's a reminder that the zone of avoidance isn't just a challenge to overcome. It's a laboratory for innovation, pushing astronomers to develop tools that might one day unveil the universe's darkest secrets. Among the shadowy realms of the zone of avoidance, few discoveries have captivated astronomers as much as Dwingeloo, a galaxy hiding in plain sight just 10 million light-years away, yet completely invisible to optical telescopes until the 1990s. Named after the Dutch radio observatory that spotted it, this barred spiral galaxy is a cosmic doppelganger of our own Milky Way, complete with swirling arms and a bustling disk of stars. But here's what makes it extraordinary. It's lurking almost directly behind the Milky Way's crowded plain, its light smothered by our galaxy's dust so thoroughly that even its brightest stars were undetectable. Only by tuning into the faint radio whispers of its hydrogen gas did researchers finally pull it from obscurity. Dwingeloo isn't just a hidden neighbor, it's a time capsule. Its isolation, untouched by nearby galaxies for billions of years, has preserved a pristine snapshot of how spiral galaxies evolve in solitude. Unlike the Milky Way, which has been shaped by collisions with smaller galaxies like the Sagittarius dwarf, Dwingeloo symmetrical structure suggests a quiet, undisturbed existence. Yet it's not alone. Further surveys revealed Dwingeloo, a smaller companion galaxy orbiting it like a moon, their gravitational dance playing out unseen behind the Milky Way's glare. Together, they form a miniature galactic group, a hidden mirror to our own local group, reminding us that even in the zone of avoidance, the universe repeats its patterns. Then there's the Norma cluster, a beast of a different nature. Nestled near the galactic center, where the Milky Way's dust is thickest, this cluster is a maelstrom of X-rays and gravity. While optical telescopes see only a hazy smudge, X-ray observatories like Chandra reveal a cauldron of superheated gas, shimmering at millions of degrees as it's squeezed by the cluster's immense mass. The Norma cluster isn't just a collection of galaxies, it's a gravitational anchor, one of the most massive structures in our cosmic backyard. Its central galaxy, Norma A, hosts a supermassive black hole spewing jets of plasma so powerful they punch through intergalactic space, visible only because their X-rays pierce the dust that stifles visible light. What makes these galaxies so pivotal isn't just their concealment, it's how they defy expectations. The Norma cluster, for instance, sits uncomfortably close to the Great Attractor, its gravity contributing to the mysterious pull that's dragging our galaxy toward it. And Dwingeloo, one's pristine state, challenges assumptions about how often galaxies interact in the local universe. These aren't just curiosities, they're clues to larger cosmic truths. The Zone of Avoidance doesn't just hide galaxies, it hides galaxies that don't fit the mold, outliers that force us to rethink the rules. The deeper we probe, the more anomalies emerge. Take Hizoa J083643, a galaxy so rich in hydrogen it's essentially a cosmic gas tank, its reserves untouched by star formation. Or the bizarre IC408, a galaxy caught mid-collision, its spiral arms twisted into chaotic streams by an encounter we'd have never witnessed if not for infrared eyes. Each discovery peels back another layer of the zone's secrets, proving that what we once called a void is actually a crossroads, a place where the universe stacks its oddities just out of sight, waiting for us to look in the right way. The cosmic web is the universe's grand architecture, an intricate network of filaments that weave galaxies together like threads in a tapestry, spanning billions of light years. But what happens when a crucial section of this web lies hidden behind the Milky Way's blinding glow? The Zone of Avoidance doesn't just obscure individual galaxies, it potentially masks entire strands of this cosmic scaffolding, distorting our understanding of how matter is distributed across the universe. Imagine tracing the outline of a city's subway system, only to realize entire train lines run beneath a giant, unmarked construction site. Astronomers face a similar challenge. The cosmic web's filaments are highways of dark matter and gas, funneling galaxies into clusters and superclusters. Yet where the Zone of Avoidance crosses these filaments, our maps show gaps, phantom dead ends that might not exist at all. Some of the most massive structures, like the Pisces-Cetus supercluster complex, appear to abruptly terminate at the zone's edge, as if sliced off by an invisible blade. But simulations suggest these filaments don't just stop, they likely continue behind the Milky Way, their paths warped by gravity we can't yet measure. This isn't just a cartographic headache, it's a cosmic missing link problem. Filaments dictate how galaxies move, how they collide, even how they're born. If we can't see critical junctions in this network, we're like biologists trying to understand an ecosystem while ignoring half its food chain. Take the Sloan Great Wall, one of the largest known structures in the universe. Its full scale was only recognized when astronomers accounted for obscured regions, revealing a filament stretching over 1.3 billion light-years. What other record breakers might the Zone of Avoidance still conceal? The stakes are even higher when it comes to dark matter. Filaments are saturated with this mysterious substance, their gravitational pull shaping the universe's expansion. But if the densest knots of dark matter lie hidden in the zone, our models of cosmic evolution might be missing pivotal variables. It's like trying to predict weather patterns without knowing where the mountains are. You'll miss the storms brewing in the valleys. Efforts to reconstruct these hidden pathways are pushing astronomy to its limits. Scientists now use gravitational lensing, subtle bends in light from distant quasars, to trace the invisible mass of obscured filaments. Other teams map galaxy flows, watching how entire clusters drift toward areas of unseen gravity, like iron filings tugged toward a magnet wrapped in cloth. Each workaround reveals another fragment of the cosmic web's hidden geometry, hinting at filaments so vast they could redefine our place in the universe's structure. The zone of avoidance isn't just blocking our view, it's forcing us to rethink how we see. Every time we peel back another layer of the Milky Way's veil, we don't just find missing pieces of the cosmic web, we uncover rules of the universe we never thought to question. Dark matter doesn't glow, reflect, or emit any light, yet its gravitational grip shapes the entire universe. And if there's one place where its influence might be rewriting cosmic rules, it's the zone of avoidance. Picture an invisible hand tugging at galaxies, bending the paths of light itself, all while hidden behind the Milky Way's starry curtain. That's the enigma astronomers face when probing this region, gravitational lensing studies, where light from distant objects warps around unseen mass have revealed anomalies suggesting colossal dark matter structures lurking just out of view. One of the most compelling clues comes from something called galaxy flow. Across the universe, galaxies move not just with the expansion of space but in subtle streams, pulled by the gravity of nearby superclusters. But near the zone of avoidance, something's off. Galaxies are drifting faster than expected, as if tugged by an unseen force. It's like watching leaves floating down a river, only to see them suddenly accelerate toward an invisible whirlpool. Simulations point to dark matter filaments, massive, thread-like structures snaking through the Zone, their gravity orchestrating this motion. The catch: we can't see them directly. To map the invisible, scientists turn to gravitational lensing. When light from a distant quasar or galaxy passes near a dense concentration of mass, like a dark matter filament, it bends, creating distorted or multiple images. By analyzing these cosmic mirages, researchers reconstruct the hidden mass causing them. In the Zone, these distortions are more pronounced than anywhere else, hinting at dark matter densities that defy expectations. One study using the Hubble Space Telescope found lensing effects so extreme they implied structures 5 times more massive than the largest known superclusters. The implications ripple across cosmology. If the Zone conceals such staggering amounts of dark matter, our maps of the cosmic web, the large-scale structure of the universe, are missing critical junctions. It's like trying to navigate a city with half the roads erased from the map. Some theorists speculate these hidden knots could even challenge our understanding of dark matter itself. Could certain particles clump differently than models predict? Or is there an entire shadow universe of dark galaxies, their stars replaced by exotic matter? What makes the Zone's dark matter uniquely tantalizing is its location. The Milky Way's disk doesn't just block light, it warps the very gravitational signals astronomers rely on. Untangling these effects requires next-generation tools. The upcoming Vera Rubin Observatory, for instance, will scan the entire sky with unprecedented precision, measuring subtle lensing patterns that might reveal the Zone's hidden architecture. Meanwhile, radio arrays like the Square Kilometre Array will hunt for dark matter's faint imprint on hydrogen gas distribution. The zone of avoidance isn't just a blind spot, it's a cosmic hall of mirrors where every distortion reflects a deeper mystery. As we peel back the layers, we're not just mapping dark matter, we're testing the limits of our understanding of gravity, structure, and the invisible scaffolding that holds the universe together. And if history is any guide, the answers we find might be stranger than anything we've yet imagined. Imagine trying to complete a jigsaw puzzle where 20% of the pieces are missing. No matter how skilled you are, the final picture will always be incomplete. That's the challenge astronomers face when studying the universe's large-scale structure while the zone of avoidance remains partially obscured. This cosmic blind spot doesn't just hide individual galaxies, it warps our entire perception of how matter is distributed across the cosmos, introducing biases that ripple through every model of the universe's evolution. Take galaxy surveys, for example. These sprawling maps, which catalog millions of galaxies to trace the cosmic web, rely on the assumption that what we see is representative of the whole. But when an entire swath of the sky is systematically excluded, or worse, filled with guesswork, the data becomes skewed. It's like taking a census but ignoring every fifth neighborhood, then assuming the results reflect the entire city. For decades, this omission distorted our understanding of galactic clusters, making some regions appear emptier than they truly are while overestimating the density of others. The consequences aren't just academic, they affect everything from measuring the universe's expansion rate to testing theories of dark matter. One stark example is the so-called local hole, a region spanning nearly 1 billion light-years where galaxies seemed unusually sparse. Early surveys suggested it might be evidence of a cosmic void, a rare underdensity in the universe's fabric. But when astronomers accounted for galaxies hidden in the zone of avoidance, the hole shrank dramatically. Many of those missing galaxies were there all along, just camouflaged behind the Milky Way's dust. This revelation didn't just correct a map, it challenged assumptions about how evenly matter is distributed, forcing scientists to recalibrate models of cosmic evolution. The Zoe's shadow extends even to dark energy research. To measure the universe's accelerating expansion, astronomers rely on supernova and galaxy distributions as cosmic mile markers. But if entire clusters are missing from the dataset, those calculations can drift off course. A 2018 study found that ignoring the ZOE introduced errors of up to 5% in dark energy measurements, a margin that might seem small, but in cosmology, where precision is everything, it's enough to tilt the balance between competing theories. Perhaps most intriguing is how the ZOE biases our view of the cosmic web itself. Simulations predict that filaments of dark matter and gas should connect galaxies in a predictable, lattice-like pattern. Yet when astronomers compare these models to observations, the filaments near the ZOE often seem truncated or misaligned. The reason? Hidden mass. Galaxies concealed by the Milky Way's disk are still exerting gravitational pull on their neighbors, bending the apparent paths of those we can see. It's like watching puppets dance without realizing some strings lead offstage into the shadows. The solution isn't just adding more data, it's rethinking how we gather it. Modern surveys like the 2-micron all-sky survey 2MASS now combine infrared, radio, and X-ray observations to fill in the ZOE's gaps, stitching together a more complete tapestry. Machine learning algorithms help predict where hidden galaxies likely reside based on their gravitational fingerprints. And projects like the Vera Rubin Observatory's Legacy Survey of Space and Time promise to map the sky with unprecedented depth, turning the zone of avoidance from a liability into a frontier. What makes this more than a technical fix is what it reveals about scientific humility. The ZOE reminds us that every observation is framed by our vantage point, not just in space but in time and technology. The universe isn't hiding its secrets deliberately, we're just learning how to ask the right questions. And with every patch of the zone we illuminate, we're not just correcting old maps, we're redrawing the boundaries of what's possible to know. The next leap in unraveling the zone of avoidance won't come from incremental upgrades. It'll be driven by telescopes so advanced they'll make today's observatories look like handheld binoculars. Leading the charge is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Unlike Hubble, which peers through a narrow keyhole of the sky, Roman will wield a field of view 100 times wider, capturing vast swaths of the ZOE in a single sweep. But its real superpower lies in infrared vision, sharp enough to cut through the Milky Way's dust like a heat-seeking scalpel. Roman won't just spot hidden galaxies, It'll map their precise shapes, colors, and even the ages of their stars, revealing how these obscured systems evolved in isolation. Imagine uncovering a lost chapter of galactic history, written in light we've never been able to read until now. Then there's the Square Kilometre Array, or SCAR radio telescope, so vast it spans 2 continents, with thousands of antennas scattered across South Africa and Australia. When completed in the late 2020s, SKA will detect hydrogen gas emissions with such sensitivity it could pick up a galaxy's faint whisper from the dawn of time. For the Zone of Avoidance, this is a game changer. SKA won't just find hidden galaxies, it'll trace the invisible rivers of gas connecting them, exposing the cosmic web's hidden scaffolding. Picture mapping a jungle not by its trees, but by the roots weaving beneath the soil. SKA's data could finally answer whether the ZOA conceals dark matter, filaments dense enough to bend our models of gravity itself. But the real magic happens when these instruments team up. Roman's infrared eyes and SKA's radio ears will cross-examine the ZOA in wavelengths that complement each other perfectly. Where one sees starlight filtered through dust, the other detects the cold hydrogen fueling future stars. Together, they'll create a stereoscopic view of the universe's blind spot, like sonar and night vision goggles used simultaneously. Early targets include the so-called Dark Galileo object, a mysterious radio source near the galactic center that might be a primordial black hole or an entirely new class of obscured quasar. Yet the most tantalizing prospect isn't just filling gaps in our maps, it's discovering anomalies that defy current physics. The ZOA's obscurity makes it the perfect hiding place for cosmic oddities, rogue supermassive black holes drifting between galaxies or dark galaxies made almost entirely of unseen matter. With Roman and SKA, we're not just lifting a veil, we're setting traps for the universe's best-kept secrets. And if history's any guide, the ZOA's biggest revelations won't be the ones we're expecting. They'll be the truths we haven't even thought to question yet. Among the most exciting breakthroughs in exploring the Zone of Avoidance isn't happening in high-tech labs or elite observatories. It's unfolding on the laptops and tablets of everyday people around the world. Citizen science projects have turned curious amateurs into cosmic detectives, sifting through data too vast for any single team of astronomers to tackle alone. Platforms like Zooniverse invite volunteers to scan infrared images, spotting hidden galaxies masked by the Milky Way's glare, one click at a time. It's a collaboration that's reshaped how we uncover the universe's secrets, proving that you don't need a PhD to push the boundaries of discovery. Take the Galaxy Zoo Hubble project, which expanded into the ZOA's infrared data. Thousands of participants classified strange, dusty objects in telescope images, flagging anomalies professionals might have overlooked. One volunteer, scrolling through cosmic static on a lunch break, noticed a faint smudge that turned out to be a dwarf galaxy, now catalogued as a vital piece of the local galactic neighborhood. These crowd-sourced discoveries aren't just novelties, they're filling gaps in three-dimensional maps of the universe, revealing how hidden galaxies fit into the cosmic web. The beauty of these projects lies in their simplicity. Volunteers aren't left guessing, they're trained through intuitive tutorials that teach them to distinguish spiral arms from elliptical blurs or spot the telltale glow of merging galaxies. Each classification gets reviewed by multiple users, creating a consensus that rivals expert analysis, and the data isn't just busy work. When the public classified galaxies from the 2-micron all-sky survey, they helped identify over 300 previously uncatalogued systems in the ZOA, some with bizarre properties suggesting they'd been isolated for billions of years. But the real power of citizen science isn't just in processing power. It's in pattern recognition. Human eyes excel at noticing the unexpected, like odd asymmetries or unusual dust lanes that algorithms might dismiss as noise. In one striking case, amateur classifiers flagged a series of oddly aligned galaxies near the ZOA's edge, sparking a professional study that revealed a hidden filament of dark matter tugging them into alignment. These accidental discoveries remind us that the zone of avoidance isn't just hiding galaxies, it's concealing subtle cosmic clues waiting for anyone patient enough to look. Beyond Zooniverse, projects like Radio Galaxy Zoo harness the public's help, linking radio emissions to their infrared counterparts, untangling which blobs in the zoo are galaxies and which are distant quasars. Others, like Backyard Worlds, task users with spotting faint, fast-moving objects that could be rogue planets or failed stars drifting through the Milky Way's foreground. Every click contributes to a living atlas of the obscured universe, one where amateur enthusiasm and professional rigor collide to illuminate the darkness. What makes this movement so revolutionary isn't just the science, it's the philosophy. The zone of avoidance, once dismissed as a professional dead end, has become a shared frontier. A teacher in Nairobi, a retiree in Oslo, and a student in Buenos Aires can all stumble upon something no one's seen before, proving that curiosity is the most universal tool we have for understanding the cosmos. And as telescopes like the Vera Rubin Observatory come online, generating more data in a week than Hubble did in decades, these volunteer networks will be the unsung heroes turning the ZOA's shadows into a new golden age of discovery. The zone of avoidance has long been a playground for storytellers, a cosmic blank canvas where science fiction can paint its wildest mysteries. In video games like Mass Effect, the ZOA becomes the perfect stand-in for uncharted space, a lawless frontier where rogue AI threats, ancient alien ruins, or even parallel dimensions might lurk. The game's Attican Traverse mirrors real-life astronomical frustration, a region so clogged with stellar debris that navigation feels like threading a needle. But here, fiction takes liberties. Where real astronomers see obscured galaxies, writers drop shadowy civilizations like the Rachni, a hive-mind species waiting to be unearthed from the cosmic dark. It's a clever twist, turning scientific limitation into narrative gold. Films have leaned into the ZOA's mystique even more boldly. The 2016 movie Arrival subtly nods to it with its enigmatic alien ships appearing in random global locations, echoing how hidden celestial objects might suddenly appear once we look beyond galactic dust. Meanwhile, Event Horizon dials the horror up to 11, framing the ZOA as a literal hellscape where a lost spaceship breaches a dimension of unspeakable terror. The real ZOA isn't a portal to hell, of course, but the metaphor works because it taps into our primal fear of the unknown. What could be hiding where we can't see? Fiction's answer is always more thrilling than reality's. Literature takes a more philosophical approach. Alastair Reynolds' Revelation Space series imagines the ZOA as a dumping ground for cosmic horrors, a place where ancient civilizations hid their mistakes. It's a trope that mirrors humanity's own history. Unexplored maps once bore warnings like "Here be dragons." Even the Three-Body Problem trilogy flirts with the idea, suggesting an alien fleet might use the Milky Way's dust clouds as camouflage during an invasion. These stories resonate because they weaponize human curiosity. The ZOA isn't just a scientific hurdle, it's the universe's ultimate locked door, and every knock triggers a what-if scenario wilder than the last. What makes these portrayals so compelling is how they invert reality. In science, the ZOA is a technical challenge, a filter to overcome. In fiction, it's a deliberate enigma, as if the cosmos itself is keeping secrets. That duality reflects our relationship with the unknown, equal parts frustration and wonder. Whether it's video games hiding boss battles in the dust or novels tucking doomsday devices behind celestial static, the ZOA endures as fiction's favorite cosmic blind spot because in the shadows anything is possible. Even as astronomers peel back the layers of the zone of avoidance, fierce debates rage over what this cosmic blind spot truly represents. One of the most heated controversies centers on the idea of a supervoid, a hypothetical region spanning hundreds of millions of light years where galaxies are mysteriously sparse. Some researchers argue the ZOA's apparent emptiness isn't just an illusion created by the Milky Way's dust. They propose it might be one of the largest underdense regions in the universe, a cosmic desert defying our understanding of how matter clusters. Others dismiss this as observational bias, insisting that better tools will eventually reveal galaxies lurking in the shadows. The supervoid theory gained traction when surveys showed unusual temperature dips in the cosmic microwave background, the afterglow of the Big Bang, aligned with the ZOA. These cold spots, some argue, could be the imprint of a vast emptiness stretching across the sky, where the lack of galaxies subtly cools the surrounding universe. Proponents point to the analogous KBC void, a known underdensity surrounding our local group of galaxies, as evidence that such structures exist. If the ZOA conceals a void even larger than KBC, it would challenge the cosmological principle, the foundational idea that matter is evenly distributed on the largest scales. Skeptics counter that these anomalies are just artifacts of incomplete data. They highlight how early maps of the ZOA, based solely on optical telescopes, falsely suggested empty regions that later radio and infrared surveys proved were teeming with galaxies. The Planck satellite's detailed cosmic microwave data, for instance, shows no definitive proof of a supervoid aligned with the ZOA. Instead, the cold spots might stem from foreground interference, dust in our own galaxy, subtly distorting the microwave signal like static on a radio. The debate turns philosophical when it comes to missing mass. If the ZOA were truly a void, simulations suggest surrounding galaxies should rush to fill the underdensity, creating detectable flows of motion. Yet observed galaxy movements near the ZOA show no such pattern. This paradox has led to a radical third camp, the idea that the ZOA's emptiness might actually hide an excess of dark matter, its gravity warping our measurements to mimic a void. It's a cosmic sleight of hand. What looks like nothing could be a knot of invisible mass, twisting the rules of the game. What makes this more than academic sparring is how it reflects astronomy's core struggle, distinguishing signal from noise in a universe that refuses to sit still. The ZOA forces us to question whether we're seeing gaps in the cosmic web or gaps in our own perception. Every new telescope that peers into this zone doesn't just settle old arguments, it sparks new ones, proving that in the hunt for universal truths, even emptiness can be full of surprises. The Zone of Avoidance isn't the universe's only cosmic oddity. It's part of a broader menagerie of mysteries that challenge our understanding of space. Take dark flow, for instance, the unsettling discovery that entire galaxy clusters are drifting in the same direction at inexplicable speeds, as if pulled by some unseen force beyond the observable universe. While the ZOA obscures objects behind our galaxy's dust, dark flow hints at influences from outside our cosmic horizon. Both phenomena force astronomers to confront the same humbling truth. We're missing vast pieces of the cosmic puzzle, whether they're hidden in our blind spot or beyond our sightlines entirely. Then there's the KBC void, a gargantuan bubble of relative emptiness where our Milky Way resides. Stretching over 2 billion light-years, this underdensity flips the ZOA's script. Instead of hiding galaxies behind a wall of stars, it's a genuine cosmic desert where matter is strangely sparse. At first glance, they seem like opposites, one an illusion of obstruction, the other a real absence, but dig deeper and the parallels emerge. Both distort our local measurements of the universe's expansion, skewing data in ways that spark heated debates. The KBC void might explain why some calculations of Hubble's constant disagree, just as the ZOA's hidden mass could be throwing off our galactic census. Together, they're reminders that our corner of space might be the statistical outlier, not the norm. Even more provocative is how these mysteries intersect. The Great Attractor, lurking in the Zoe's depths, contributes to Dark Flow's galaxy tug-of-war, while the KBC Void's gravity subtly amplifies the motion. It's as if the universe is weaving these enigmas into a single, interconnected web, one where local voids and obscured superclusters dance in a delicate gravitational balance. The Zoe stands out because it's our blind spot, but it's hardly alone. Across the cosmos, from the CMB cold spot to Boots Void, we keep finding regions that defy expectations, each with its own story of missing mass or unexpected structure. What makes the Zoe unique isn't just its concealment, it's the sheer audacity of its hiding place. While other mysteries lurk in the distant universe or the primordial past, the Zone of Avoidance taunts us from our own backyard, a reminder that the cosmos reserves its boldest secrets for the places we least think to look. Could the Zone of Avoidance be more than just a cosmic blind spot? Could it be a portal to quantum mysteries we've barely begun to fathom? Some theorists are daring to ask whether the Zoe's peculiar properties might make it a testing ground for radical ideas, like quantum entanglement operating across galactic distances. Picture two particles linked instantaneously, no matter how far apart, a phenomenon Einstein famously dismissed as spooky action at a distance. Now imagine scaling that up. What if entire galaxies hidden behind the Zoe are subtly influencing the ones we can see through quantum connections we don't yet understand? It's a wild idea, but not without precedent. Experiments on Earth have shown entangled particles coordinating their states faster than light could travel between them. If quantum weirdness can defy local physics here, why couldn't it leave faint fingerprints in the obscured relationships between galaxies? Then there's the multiverse angle. Some speculative models suggest the Zoe's gravitational anomalies, like the Great Attractor's inexplicable pull, might be shadows of parallel universes brushing against our own. In these theories, the Milky Way's dust wouldn't just be blocking light. It could be masking subtle space-time ripples from neighboring cosmic bubbles. Think of it like hearing muffled voices through a thick wall. You can't make out the words, but you know something is there. The math gets dizzying fast. If other universes with different physical constants exist, their gravity might leak into ours, warping galaxy motions in ways that conventional dark matter can't fully explain. The Zoe, with its stubborn opacity, becomes the perfect hiding place for such phantom influences. Of course, mainstream cosmology treats these ideas with healthy skepticism. Quantum effects typically vanish at macroscopic scales, and multiverses remain firmly in the realm of untested conjecture. Yet the Zoe's resistance to conventional observation keeps these hypotheses alive. When traditional tools fail, imagination rushes in, and history shows that today's fringe idea can become tomorrow's breakthrough. After all, black holes and dark matter were once dismissed as mathematical oddities before evidence forced them into textbooks. What makes the Zoe uniquely tantalizing for these theories is its dual nature. It's both empty and overflowing, empty of traditional data, yet overflowing with gravitational anomalies that beg for explanation. Whether quantum or multiverse hypotheses ever gain traction, they underscore a deeper truth. The universe's greatest puzzles often lie not in the light, but in the shadows we've yet to illuminate. And until we can peer deeper into the Zone of Avoidance, it will remain a canvas for both rigorous science and bold speculation, where the line between them blurs like starlight through dust. What if, hidden behind the Milky Way's dusty curtain, entire galaxies are teeming with life we can't even imagine? The Zone of Avoidance doesn't just obscure stars, it may be hiding cosmic petri dishes where biology experiments with forms we've never seen. Consider this: galaxies buried in the Zoe have evolved in near-total isolation, shielded not just from our telescopes, but from the gravitational chaos that shapes galaxies in more visible regions. Without frequent collisions or disruptions, their planetary systems could enjoy extraordinary stability, billions of uninterrupted years for life to emerge, adapt, and perhaps even surpass our own complexity. Take the hypothetical Dwingeloo 3, a pretend cousin to the real Dwingeloo galaxies. If it exists, it might float undisturbed in the Zoe's quiet outskirts, its planets orbiting ancient suns with clockwork precision. On a world there, seasons could last millennia, allowing life to develop rhythms and metabolisms utterly alien to Earth's frantic pace. Or picture a rogue planet kicked loose from its star and drifting through the interstellar dark, warmed only by geothermal vents. In the Zoe's shadows, such nomads untethered from stellar heat might harbor subsurface oceans where chemistry dances in ways sunlight-dependent life couldn't fathom. The real intrigue lies in the Zoe's potential for extreme environments. Galaxies here might be rich in pristine gas uncontaminated by heavy elements from frequent supernova. In these primordial nurseries, stars could form with radically different planetary ingredients, birthing worlds where silicon, not carbon, forms the backbone of biology. Or consider black hole-driven ecosystems. The Zoe's hidden quasars could bathe planets in relentless radiation, prompting life to armor itself in bioluminescent shields or harness exotic energy sources. Astrobiologists have long speculated that life thrives in diversity around pulsars in methane lakes, even in the vacuum of space. The Zoe offers a tantalizing twist. What if the most alien life isn't in distant galaxies but right next door, buried under our own galaxy's dusty veil? Until we peer deeper, the Zone of Avoidance remains the universe's ultimate locked garden, its secrets waiting not in some far-off corner of the cosmos, but just out of sight, in the blind spot we've yet to illuminate. Mapping the Zone of Avoidance isn't just about filling in blank spots on our cosmic maps. It could hold the key to understanding how the entire universe will end. Right now, cosmologists are locked in a debate over two possible fates for our cosmos. The Big Crunch, where gravity pulls everything back into a singularity, or the heat death, where the universe expands into infinite cold emptiness. The deciding factor, dark energy, the mysterious force accelerating the universe's expansion. But here's the catch. Our measurements of dark energy's strength might be skewed because we're missing critical data from the Zoe's hidden galaxies and clusters. Think of it like trying to predict the weather while ignoring an entire ocean. The Zoe's concealed structures could be warping space-time in ways we can't yet measure, subtly altering the cosmic tug-of-war between dark energy and gravity. For instance, if the zone hides more superclusters like the Great Attractor than we've accounted for, their collective gravity might be slowing the universe's expansion more than current models suggest. On the flip side, if it's peppered with vast voids, their absence of gravitational pull could let dark energy dominate even faster, hastening the universe's march toward heat death. The difference hinges on percentages so small they'd fit in a rounding error, but in cosmology, those decimals dictate destiny. This isn't just theoretical hand-waving. The Planck satellite's cosmic microwave background data already shows odd temperature fluctuations aligned with the Zoe, hinting at hidden mass distorting the universe's earliest light. If future telescopes like the Nancy Grace Roman or the Square Kilometre Array reveal that the Zoe's hidden structures are denser than we thought, it could tilt the scales toward a Big Crunch scenario. Alternatively, if they uncover sprawling voids, it might confirm that dark energy is unstoppable. Some simulations even suggest the Zoe could harbor dark energy fossils, ancient regions where this repulsive force clumped like cosmic froth, leaving imprints on galactic motions. The stakes are cosmic. Every galaxy cluster we uncover in the Zoe adds weight to one side of the equation, refining our predictions down to razor-thin margins. It's like adding missing pieces to a puzzle only to realize they change the whole picture. And while we may never witness the universe's final act, understanding the Zoe's role ensures our forecasts aren't just guesses. They're grounded in the full tapestry of the cosmos, not just the parts we can see. Exploring the Zone of Avoidance isn't just a scientific challenge, it's an ethical dilemma. With limited funding, telescope time, and human effort, every hour spent peering into this cosmic blind spot is an hour not spent studying black holes, exoplanets, or the origins of life. The question isn't just whether we can uncover the ZOA's secrets, but whether we should prioritize them over other frontiers. On one side, skeptics argue that the ZOA's obscurity makes it a poor investment. Why pour resources into a region where every observation requires 10 times the effort, when clearer patches of sky offer quicker breakthroughs? The Hubble Space Telescope, for instance, could spend weeks staring at the ZOA only to capture blurry smudges, while the same time invested elsewhere might reveal the atmospheres of distant worlds or the death throes of ancient stars. Yet dismissing the ZOA as too difficult ignores the lessons of history. Astronomy's greatest leaps often come from tackling the inconvenient, not the obvious. Think of Vera Rubin's stubborn pursuit of galaxy rotation curves, which led to the discovery of dark matter despite initial skepticism, or the decades-long hunt for gravitational waves, once mocked as a fool's errand. The ZOA's challenges aren't unique, they're part of a tradition where the hardest problems yield the most transformative answers. The galaxies hiding there could rewrite our understanding of cosmic structure, and the dark matter anomalies might hold clues to gravity itself. Ignoring the ZOA risks leaving gaping holes in our cosmic maps, like charting Earth's continents but deliberately skipping the Pacific. There's also the question of balance. The ZOA doesn't demand all our attention, just a fair share. Modern observatories like the Vera Rubin telescope and the Square Kilometre Array are designed to survey the entire sky, ZOA included, with minimal extra cost. These projects don't force an either-or choice. They bake the ZOA into their mission, ensuring no region is left behind. Smaller, targeted studies can then follow up on anomalies, creating a cost-effective pipeline from discovery to deeper study. It's not about diverting resources from other fields, but about integrating the ZOA into the broader tapestry of exploration. The ethical stakes go beyond telescopes and budgets. The ZOA represents a philosophical stance. Do we accept the universe's mysteries when they're inconvenient, or do we insist on seeing everything? Past generations might have dismissed the ocean depths or the Earth's poles as too hostile to explore, until we did, and redefined biology and climate science in the process. The ZOA is no different. Its dust clouds might conceal answers to questions we haven't even thought to ask yet. In the end, the choice isn't just about science. It's about curiosity itself. Funding the ZOA's exploration sends a message that no corner of the cosmos is off-limits, no matter how stubbornly it resists our gaze. The universe doesn't owe us easy answers, but that's never stopped us from looking. Close your eyes for a moment and picture this. We're dialing down the Milky Way's opacity like adjusting a cosmic dimmer switch. The thick bands of dust dissolve, revealing a spectacle no human has witnessed directly. The zone of avoidance, not as a void, but as a fireworks display of galaxies. First, the foreground clears. Our own galaxy's stars fade to transparency, like stepping back from a fogged-up window. Suddenly, the empty patches erupt with color. Sapphire spirals pinwheeling in the dark, golden ellipticals glowing like embers, and ruby-red starburst galaxies seething with newborn stars. Now let's zoom toward one of the ZOA's crown jewels, the Vela supercluster. In this simulation, its true scale becomes horrifyingly beautiful. Hundreds of galaxies swarm like fireflies caught in gravity's web, their collective mass bending spacetime into a shimmering lens. Fly past NGC 3256, a cosmic wreck where two spirals collide in slow motion, trailing blue tendrils of orphaned stars. The violence is mesmerizing. Supernovas flash like camera bulbs, while black holes whirling at the centers siphon gas into glowing accretion disks hotter than 1,000 suns. But the real shock comes when we pivot toward the Great Attractor. No longer hidden, it reveals itself as a galactic megalopolis, a sprawling hub where thousands of galaxies spiral inward like water down a drain. At its heart, a monstrous elliptical galaxy devours its neighbors, growing fat on stellar cannibalism. Gravitational waves ripple outward from mergers, warping the view like funhouse mirrors. The attractor's pull isn't just theory here. We see it: streams of galaxies stretched into comet-like tails as they plunge toward the core. Suddenly, the simulation throws us a curveball. Between two familiar galaxy clusters, an anomaly flickers, a structure that shouldn't exist. Dubbed the vein by researchers, this filament of dwarf galaxies stitches across the Zone are in near-perfect alignment, defying models of cosmic web formation. Some galaxies along this chain spin backward, their retrograde motion hinting at ancient collisions or dark matter's invisible hand. It's a reminder that even in a simulated universe, the Zone guards surprises. As we pull back to refog the view, the lesson lingers. This isn't just eye candy, it's a manifesto for curiosity. Every translucent galaxy in this simulation represents real data, painstakingly pieced together from radio whispers and infrared echoes. The Zone's true beauty isn't in the hypothetical clarity we've just enjoyed, but in the stubborn ingenuity required to unveil its secrets one wavelength at a time. The simulation fades, but the question remains: what else is cloaked in the darkness, waiting for us to invent new ways of seeing? With all these mind-bending theories and discoveries swirling around the Zone of Avoidance, here's where you come in. What do you think is hiding behind the Milky Way's dusty curtain? Maybe you're convinced there's a colossal alien megastructure quietly harvesting energy from stars we can't even see. Or perhaps you've got a wild hunch that the Zone is cosmic camouflage, nature's way of keeping something big off our radar until we're ready to discover it. Drop your most imaginative or scientifically grounded theories in the comments. This is one mystery where the crowd might just outshine the experts. And hey, if you're feeling stuck for ideas, let's kick things off with a few possibilities. Could the Zone be the universe's way of hiding its own flaws? A glitch in the cosmic code where galaxies didn't form quite right? Or what if it's the opposite, a treasure trove of pristine, undisturbed galaxies, frozen in time like insects in amber? Some of you might even argue that the Great Attractor isn't just a cluster, it's a gravitational footprint left by something else passing through our universe. Here's the fun part: no guess is too outlandish. After all, some of history's biggest breakthroughs started as crazy ideas. So whether you're team hidden black hole civilization or team interdimensional rift, tell us what's lurking in the shadows and why you're convinced it's there. Who knows, your comment might just inspire the next big telescope proposal, or at least spark a debate that keeps us all staring at the stars a little longer. The Zone of Avoidance isn't just a blank spot on our cosmic map, it's a missing chapter in the story of the universe. Think of it like reading a novel with every fifth page torn out. You might grasp the plot, but the nuances, the twists, the full depth of the narrative, those are lost without those crucial pages. The Zone is the same. Every galaxy hidden behind the Milky Way's glare, every filament of dark matter we can't yet trace, represents a piece of the puzzle that could redefine how galaxies form, collide, and evolve. This isn't about filling in gaps for the sake of completeness. It's about confronting the biases in our very understanding of the cosmos. Consider what we've learned so far from the fragments we've uncovered. The Dwingeloo galaxies revealed that massive, undisturbed spirals could thrive in isolation, challenging assumptions about galactic interactions. The Great Attractor showed us that the largest gravitational forces in our neighborhood might be invisible to traditional telescopes. And the Vela supercluster proved that entire galactic metropolises could hide in plain sight, warping the motions of galaxies we can see. Each discovery from the Zone doesn't just add to our knowledge, it forces us to recalibrate our models. If structures like these exist in the sliver we've explored, What does that say about the regions still shrouded in dust? But the ZOA significance goes deeper than cataloging hidden galaxies. It's a testbed for our tools and theories. The techniques developed to pierce this cosmic veil, infrared surveys, radio astronomy, gravitational lensing, haven't just illuminated the zone, they've revolutionized how we study the entire sky. The same methods that uncovered the Norma cluster are now used to probe the atmospheres of exoplanets or map the birthplaces of stars. In pushing the limits of observation to conquer the ZOA, we've accidentally equipped ourselves to explore farther and fainter than ever before. Perhaps most profoundly, the Zone of Avoidance is a reminder of humility. For all our towering telescopes and supercomputers, we're still creatures tethered to a single vantage point, peering out from a modest spiral galaxy's edge. The universe doesn't owe us a clear view. We have to fight for every photon, every radio whisper, every gravitational clue. And in that fight, we're not just uncovering hidden galaxies, we're rediscovering the thrill of the unknown. The ZOA is a frontier that refuses to be tamed, a puzzle that keeps rearranging itself with every new piece we fit, and that's why it matters, not just for the answers it might hold, but for the questions we haven't even thought to ask yet. If today's deep dive into the Zone of Avoidance left you as fascinated as it left us, don't let the curiosity stop here. Hit that like button. It helps more cosmic explorers like you find these discussions, and subscribe so you never miss a journey into the universe's greatest enigmas. Want to go even deeper? Check out the links in the description for papers, interactive maps, and citizen science projects where you can join the hunt for hidden galaxies yourself. And get ready, because next time we're venturing into one of space's most unsettling riddles, the mystery of rogue black holes. Imagine invisible monsters, each weighing millions of suns, drifting silently through the cosmos, and one might be closer than we think. Until then, keep looking up. The universe has a way of hiding its best secrets just beyond the